Straightforward. Basically, we're going to weigh out samples of our unknown acid, dissolve them in water, add some phenolphthalein, and titrate them. We need to get 3 runs that agree within 1%. Since we aren't using the same amount of acid in each flask, we have to take a ratio. We'll take the mass to volume or volume to mass ratio and make sure those agree within 1%. Or you can go ahead and do the calculation. Doing the calculation for the molar mass is pretty straightforward. We weigh the grams of acid and figure out how many mils of titrant we have to get the moles of acid. The only thing is we don't know if it's a diprotic or monoprotic acid, so we have this here. How you can tell if it's a diprotic or monoprotic acid is it's on the unknown vial. There's a very important number you need to write, otherwise you cannot do the calculation. And that is if there's 1 hydrogen or 2 hydrogens. Okay. But that's the basic equation there. All right, any questions on the lab? Let's talk about last week's quiz. Last week's quiz, we have these numbers here, these percentages. And the question is, are these natural abundances mass percentages or mole percentages? And it seemed like a lot of people got it wrong. They said that these are mass percentages. And those are not mass percentages. Mass percentages are kind of inconvenient to use, What is water made up mostly of? Hydrogen or oxygen? Hydrogen or oxygen? Well, it depends. If you're talking about mass, then it's 88% oxygen, right? If you're talking about atoms, then it's 67% hydrogen. What do you think for chemists is more easy to track, in terms of composition? Mass or mole percent? For example, is it easier to represent water as H11 or let's do H12O88? Or is it easier for us to track water as H2O? H2O. Why do we use mole or atom percent when we're referring to composition? Not always, Some people will call water as being 88% oxygen, 12% hydrogen. That's okay. You can use that and people will know what you're talking about. The reason it's easier in terms is because it's easier to count atoms rather than weigh atoms. Don't you think? In certain respect. So, what I was hoping that you would do, since this was open book, is look in your book and then see, how do they get these percent natural abundances? Well, these percent natural abundances are determined using a mass spectrometer. And so if you feed a stream of atoms here, what does the mass spectrometer detect? Does it detect how many grams of atoms hits here? How many grams? And so this is kind of like a balance. There's more weight over here. Actually, the most weight is here. Let's see. Now, the way a mass spectrometer works is it detects the number of strikes. And so if this is a big peak here, that means more atoms, 1, 2, 3, 4, 5, atoms hit here versus only 1 atom. For every 1 atom that hits here, 5 atoms hit here. And so this peak is 5 times more intense than this peak. Well, there's something wrong with the scale here. This scale, they probably didn't make it accurate, of course. But the mass spectrometer determines, you know, if there are 100 atoms, how many atoms of this type do you have? How many atoms of that type? That's what we call the percent natural abundance. Right? You don't weigh them because, you know, does a hydrogen 1 atom weigh the same amount as a hydrogen 2? And so what is a mass percentage going to really tell you? I mean, already the hydrogen 2 weighs twice as much almost as the hydrogen 1. So does that mean the hydrogen 2 is, well, the hydrogen 2 must be, you know, 200% heavier than the hydrogen 1. Does that make any, that doesn't, so, you know, as far as natural abundances go, I purposely left it off, as does everybody else. Everybody else leaves it purposely off because everybody should know it's a mass percent or a mole percent? Mole percent. And so this is why, you know, there's no units on there. They don't say it because obviously they're thinking it's a mole percent, but I know based on, you know, people learning it, it's easy to confuse. Since it's easy to confuse, you know, it makes it tough. And so the way I read this is if I had, this is close to 10,000. If I had 10,000 atoms, 9,976 of those atoms would be oxygen 16, 4 of those atoms would be oxygen 17, and 20 of those atoms would be oxygen 18. Down here I'd read this, if I had 100,000 atoms, 99,985 of those would be hydrogen 1, 15 hydrogen 2s, and pretty much no hydrogen 3s. Its abundance is quite small. And so these percentages that we're working here with are mole percentages. And so I'd say only 5% of I think practically the majority of people put mass percentage. And a minority put mole percentage. All right, let's go to this one. What is the percentage of H2O16H2 here? And so this is a little challenge problem here. It's a challenge problem, but you know, it's more challenging for some and less challenging for others. It's like, did I tell you about that engineering class? You know, in the engineering class, they would always give a whole bunch of different equations. You use this equation for this equation for that, you know. And so on the test, the professor decided he's going to give us a problem in which he never gave us the equation, and the equation's not in the book. And so, you know, how do we do it? And so I looked at all the variables, and they all had their units, and then I looked at what he was asking for, which had its own units, and I thought, oh, I'll just string it together using dimensional analysis. And this is exactly what I did. But surprisingly, you know, and I thought it was an easy problem, but surprisingly, 70%, I think, you know, talking to other students in the class after the test, like 70% didn't get it. They couldn't figure it out because they weren't given the equation, right? But, you know, there weren't that many chemists because I thought, you know, if there were more chemists in this class, you know, then that, the percentage who would have gotten it would have been much higher because it was just a simple dimensional analysis problem. Well, this isn't such a simple dimensional analysis problem, and I saw that, you know, people were doing different things. But one of the things is, okay, H2 is 0.015%. You know, O16, this is 99.76%. And H2 is 0.015%. And so how can I string these together to get ultimately what I want is just percentage? You know, and so a lot of people were doing it, right? For example, they did a 0.015. This is the problem, 0.015 out of 100, you know? And so 0.015 or 15 out of, we'll move it 3 over, 15 out of 100,000 is the same as 0.015 out of 100, right? 15 out of 100,000 are H2s. And so, you know, when we're thinking about, you know, statistically, this could be an H1, H2, or H3. Well, H3 is not that common, so this is an H1. So, you know, 15 out of 100,000 are H2. that means the remainder, 999,000, are H1s. And so that's a fractional abundance of that. Over here, the same thing. If we look at this other hydrogen, it's only a 0.015 out of 100 fractional abundance. And so if we have these two fractional abundances and then just multiply this by this percentage, we don't have to do it in this order, by the way, but we could do it in any order, then this should be the percent natural abundance of this water molecule. I could have done, I could have done it, or I would have gotten the exact same answer if I did this. 0.015 out of 100 times 99.76 out of 100 times 0.015%. This would have given me the same. And so a number of people got this right, but I'd say the majority got it wrong, fortunately. Well, we get the percent here. This is a mole percent. And so what this says is, what is the number here, actually? Can someone just calculate it really quick? Does someone have it? Actually, we don't need it. To do the next part, I'll just lay it out, but not actually calculate it. How many grams of H2O16H2 are in 250 milliliter sample of water? And so we start off with 250.00 milliliters. This is 5 sig figs of H2O. And this H2O is a mixture, right? It's a mixture of a whole bunch of different ones. I didn't even give you the hard one. As far as the probabilities go, I could have given you the hard one, which is I've given on past tests. I've given the hard one. You know what the hard one is? What is, let me do a quick aside. What is the probability, in other words, what is the percent natural abundance of this? And you might go, that's not hard, we just do it the same way. And so if you do it the same way, H1 is 99.985. So we'll just go, all right, 99.985 out of 100 are H1. We could do this with the hydrogens first and then do the oxygens, since oxygen's pretty common. H2 is 0.015 out of 100. And then we'll just do 99.76%. Oh, let me back up a step. A lot of people did 2. It seems to make sense. 2 times 0.015 out of 100. This seems to make sense because we're doubling, right, the natural abundance because we got 2 of them, right? But that's not really the case because when we think about this is the fractional abundance. This is for the previous example. This is the fractional abundance, or they just added 2 of these together, so we got 0.03. But that's not correct, because in one respect, this is saying, well, 2, that would be a fractional abundance, and 2 out of 1 is 200 out of 100. So 200 out of 100 fractional abundance for one of those hydrogen isotopes. Is that right? No. And so that's another way of thinking about it. The reason why this doesn't work is because the two hydrogens aren't together. They're 2 separate hydrogens. But going back to this, is this the answer? Based on what we just did, is this true or false? The setup is correct? Unfortunately, this setup is false. Why is this wrong? The reason it's wrong is because, statistically, there's only one way of having this. You know, you have to have an H2 and an H2, right? But over here, you know, if we have a 1 and a 2, statistically there are two ways of making this. This is way number 1. Way number 2 is on this one, you know, there was some fractional probability we have an H1. But there's also a fractional probability we have an H2. And that fractional probability that we have an H2 is 0.015 out of 100. Then you go, okay, but then over here we're going to have 0.16 and an H1. So the fractional probability of this H1 is 99.985 out of 100. And then we have 0.16 and we get the exact same number. So what's the problem? You know, this would be, the algebra is commutative, so it's the same, right? Well, what the problem is since there are two ways of making this, statistically we have to double this. And so what we have to do is, in order to make up all the percentages add up to 100%, we have to account for the two ways of making this. There's only one way of making this. And so over here, yes, we'd have to double the percentage. You know, both these percentages are going to be the same because there are two ways of doing it. And so this really throws people for a loop here. But it's easy to find out because I gave them this problem on a past exam, and on the past exam I asked for all the naturally existing water molecules, and then for all the percent abundances, and then I asked for what is the total. In other words, what is the sum of all the percent abundances? Well, the sum of all the percent abundances has to add up to 100%, right? There's going to be round-off error, but if they don't account for these, then they're off by like 30%. And can you say 30% is round-off error? No. And so there's something they're missing, and so it takes some time. So this was a challenge problem on a test, you know, to figure out what's going on with the percent natural abundances since they weren't adding up to 100%. And so, you know, a challenge problem not that many people got, you know. It was a tough problem, but some people made, you know, some progress in it. Well, anyway, let's go back to this. So, you know, I purposely picked H2 to make the percent calculation straightforward. You know, and I thought about this before the quiz. I thought, nah, I'm not going to give you the H1, H2 because I haven't even talked about it. And I was thinking, too hard. All right, so we go from milliliters of water to grams of water. You know, and the conversion factor here is we use the density of water at 24.2 degrees C. And so this density you just got from the table to 6 sig figs, right? And so we got 5 sig figs here, 6 sig figs here. That's so far so good, right? It's 0.99 whatever density. So convert milliliters to grams of water. And then from grams of water, we go to moles of water. Moles of water. How do we do that? We use the molar mass. Molar mass of water is 18.02 grams per mole. All right, we'll flip it over. So we get moles on top, grams on the bottom. But is this enough sig figs? This is only 4 sig figs. Well, I told you only 2 decimal places is adequate, right? And so 101 for hydrogen times 2 is 202 plus 1600 for oxygen gives us 1802. But that's for chapter 4. This is chapter 2. In chapter 2, we're looking at isotopes and isotopic masses. Those go out to many, many decimal places, so we need much higher precision for that. A lot more sig figs, right? And so in this case, is this adequate to use 4 sig figs here when I'm given 5 sig figs there? You know, if I'm only going to use 4 sig figs here, that is, I'm going to use a cheaper periodic table, or I'm going to just round it myself, then why buy this expensive volumetric container. You know? And so it doesn't make sense. And so we should increase to at least 5 sig figs by at least 1 sig fig. So if this were 5 sig figs and this were 5 sig figs, then it's okay, right? Because I'm going to minimize round off. But here I'm maximizing round off error more than I should. But I'm going to put a little asterisk here because we don't know what the rest of the sig figs are. And so we're going to wait on this particular one. And so once we go to moles of water, then we use the percent abundance of H2O16H2. I was going to write the number here, but since nobody calculated it, it's going to look like this. It's going to be, you know, X moles of H2O16H2 for every 100 moles of what? Or maybe I should have waited until somebody calculated it. What? I heard it. Water, yeah, H2O. And so if I had 100 molecules of water, I would have this many molecules of H2O16H2 in that. It's going to be a very small number. In fact, it's point, I'll just tell you, 0.5022. And so we could put this for, there would be 22 H2, and so I need to move this 6 places. No, 1, 2, 3, 4, 5, 6, 7, 7 places. 1, 2, 3, 4, 5, 6, 7. 22. If I had what is this? 1 billion. If I had 1 billion water molecules, 22 of those would be that's what a percent natural abundance is. A percent natural abundance isn't if I had 1 billion grams of water, you know, how many grams of that would I have? It's not that low. I used to use this stuff all the time, D2O, D2, where the oxygen was the average oxygen. So the oxygen was a mix of isotopes, O16, O17, O18, but the hydrogens were isotopically pure. The oxygen was not. D2O. You could buy this stuff. I never tasted it though. Would I die if I drank it? Maybe. Looked like water. It's heavy though. Well, anyway, going back to this. Okay, so I got this. Then I get moles of we could call this D2O16. Because D, you know what D stands for? This is where D is equal to deuterium, which is H2. H2 has a name, common name, called deuterium. Most people just call it hydrogen 2, like the other isotopes, but you could call it deuterium, it's fine. Maybe most people call it deuterium. But anyway, if we have the moles, then we need the molar mass of deuterium. Okay, now how many sig figs in the percent natural abundance? How many sig figs? should put a little subscript 0 because I don't want to do any round off there. How many sig figs? There are only 2 sig figs here. If there are only 2 sig figs here, that's going to introduce a lot of round off error, so I might as well just not even care about this, right? Here, then it's acceptable. If I had, let's say, 5 sig figs here, this would be unacceptable, but since I only have 2 sig figs here, this is acceptable because already the round off error is growing quite big, so it's acceptable. What's the molar mass of D2O? Okay, here we could just figure it out. You know, I have 2 hydrogen 2s. And how much does a hydrogen 2 weigh? Going back over here, 2.0141. So that's 2 times 2.0141. And then I have an oxygen 16, which weighs 15.9949. Is that correct? 15.9949. And so D2O, or H2, hydrogen 2, O16, this is going to be, what? 282 would be 1, 7, 12, 10. 20.0271. Again. And so this is 20.0271 grams of H2O16 per mole of H2O16. So moles cancel out moles. This gives us grams of D2O16. So that's the end of that. So that's part C. And then we have part D. How many milliliters D2O16 did you just drink? So for this particular problem, I wanted to see what you would do if you're missing the information. Now obviously you could try to look it up, but we need to go from grams of D2O16 to milliliters of D2O16. What do we need? We need the density of D2O16. I'm just going to call it D because it's quicker to write than H2 sub 2. So this is where I was going to see, you know, what you would do. You know, some people would just leave it blank, as you know, the density wasn't given. You see the density, and the density was not in experiment A. You know, that was a density of water table, not the density of D2O16. But I was going to see how many people would estimate the density. You know, how many people estimated the density, knowing, well, what kind of assumption do you have to make? Well, I talked about isotopes. You know, and I asked about the chemical properties of the isotopes. For example, hydrogen 2 versus hydrogen 1. Do they have the same chemical properties, or are the chemical properties different? They have the same chemical properties, right? Hydrogen 2 versus hydrogen 1, are they about the same size, or is one twice as big? For example, is hydrogen 2 twice as big as hydrogen 1 because... Is it? No, because I said that what dictates size is the pole of the proton's positive charge for the electron's negative charge. That's what dictates the size. And so having a neutron there, does that change the amount of positive charge in the nucleus? No, so the size is about the same. And so what I wanted to see here was, I wanted to see an assumption. We're going to assume in a milliliter of water, we can pack as many D2Os as we can pack H2Os, right? Because the D2Os are about the same size, they're just heavier. And so we're going to assume that we pack it the same amount, which is a reasonable assumption, and then do this. So, you know, the density of water was what, 0.99? What was it? At 24.2. It was 0.99, etc. It's 6 sig figs. So we know the density of water is 6 sig figs. But this is the density of just H2O. H2O is mostly what? H1O16, right? And so if we assume that H2O is mostly H1O16, then what we're going to do is we're just going to do this little ratio here. And the little ratio is going to be like this. D2O16, or maybe we'll just do this. D2O16 is 20.0271. H2O is, let's do 1802. I mean, this is already, we're already making assumptions, so this isn't like an accurate calculation. And so what we're going to do is we're going to substitute out all the water and replace it with deuterium. Well, deuterium weighs a little bit, well, the D2O weighs a little bit more, D2O16, right? How much more is it going to weigh? Well, it should weigh about this factor, right? D2O versus H2O, roughly. You know, it's not perfect. I mean, you could get a more accurate number if you assume the volume is exactly the same. And so we should have a higher density here. And this higher density is what we're going to use to do the calculation from grams to milliliter. Get a little higher. Well, this last calculation is just rough, right? It's just a rough calc, and that's all you can do because you aren't given the density. If we had the density, then sure, we could just calculate it. You know, but we don't, and so we're just estimating or guesstimating the density. And therefore, we're just estimating the answer here. And so what we'd say is we just drank roughly this many milliliters of D2O16. All right, that was last week's quiz. How are your titrations coming? Are you, you know, I'm trying. I gave the morning class an option because, you know, depending on how busy you thought you were going to be for the titrations, but you have an option. This was today's quiz right here. I'll give you an option. You can take it, or you can just not take it. Just leave it. You want to take it or leave it. If you leave it, I'm not going to incorporate the points into your overall score, so you can just eliminate the total cumulative points by 5. And so the basic trade-off is this. If you think you can get a good percentage on the quiz, then you should take it because that's going to help your overall score. But if you think it's going to hurt you, then don't take it. Might as well not hurt your percentage by losing more points. So we'll take a little vote and see if you want to take this or leave it. All right, you ready to vote? How many people want to take it? Four brave people. 5. Well, unfortunately, the majority says no, so we're going to skip this quiz, and then we'll just go into lab. Okay. Your precision doesn't have to be as high for your acid. It just has to be less than 1%, right? Your unknown acid. For the oxalic acid, it has to be less than 0.5%. So you're given a little bit more wider window here. All right, that's it for discussion.